Hi, my name is Alexander and I'm going to show you how to use a distributed array capability in UV-CDAT. Now UV-CDAT stands for Ultra-Scale Visualization Climate Data Analysis Tools. It's a software developed at Lawrence Livermore National Lab, and it involves a number of other companies and laboratories, and they all contributed to the software. It's really good for looking at climate data. Now we're not actually going to use the GUI, so I'm going to quit at this point. However, we're going to use the scripting layer that comes with UV-CDAT. When you install UV-CDAT, whether you download it from the website or whether you build it yourself, you should have that capability in place right off the box. But just to be sure, we're going to check that this is the case. Alright, so we're going to let's just launch the Python interpreter. Be careful, because on many systems Python is already installed, and this is not the Python that comes with UV-CDAT. So what you really want to do is that you want to call the Python that was installed by UV-CDAT. In my case, UV-CDAT was installed under my home directory /install bin. So if I'm calling that version of the interpreter, it's very confusing, see, because they're both Python 2.7.3. They're very similar, but you can see that the installation or the build date was slightly different, and this is the version I want to use. Now you should be able to do import CDMS 2, and that command should succeed. You should also be able to do import MPI for Pi. Right? If that works, then you can just type in Control D and exit the interpreter. We're basically ready to start. Right. What are we going to do? Well, this is an example. I have a script which is called apply Laplacian to atmospheric temperature data, and I'm going to just open that script. I'm just going to go through a couple of little things that we're going to do, and just highlight the aspects that are sort of new in this presentation. First, we're going to import CDMS2. That's a very important module in UV-CDAT. You won't be able to do very much without importing that. And that allows you to open a file. In this case, it's an SCDF file that contains temperature data from the Hadley model in the UK. Once you open it, then we're going to access a variable called TAS, which is the temperature, the surface temperature. Right? So far, so good. There's nothing really new about about this aspect that existed in CDAT, the precursor of UV-CDAT. Now, what's going to change here is that we're not going to actually read the data. We're just going to access the metadata, and that's going to give us the information about the size of the variable. After that, we'll be able to apply a domain decomposition, which is a class that is now available in the dist array directory of UV-CDAT, and this domain decomposition is going to take care of, it's going to use the number of processors available on your system and the one that you use when you launch the application, and determine which domain decomposition is the most optimal. Once you have this, then we're going to read the data, but only different types, different slices of the data for every processor. So ILAT beg and ILAT end, and the same for ILON beg and ILON end, will actually vary for each processor. That's the important part, right? And after that, we're going to expose a certain halo width to our data, and that is going to allow us to access neighboring data, not only neighboring data, but just data actually stored on another processor. This is really the part that is different from the usual CDAT CDMS2 variable. We're going to apply a Laplacian to our data. That's going to enable us to perhaps detect strong gradients in our data, warm, cold front, because these are temperatures, and we're going to reconstruct that operator first locally. That is, that the data are going to work on their local slice, right? And so inside the compute domain, all the operations are going to be local. But for the data that are sort of on the border of your subdomain, we will need to do something special. And that's the part that follows. The first thing that we have to do is that we have to find out who our neighbors are. So if I'm a processor rank, then I want to know who's on to the north, to the east, to the south, and to the west. And that's this particular call. This call does not involve any communication at this point. It is just it's just about the topology of the domain decomposition. Right? There is a little bit more code here that has to be that has to handle the north and south pole, because the ranks on the north and south of the globe don't actually have any neighbors, so we have a special treatment here. Finally, we're going to fetch the data, right? And that is the only place where communication takes place. There's no other communication in this particular code except here, and we use a gather operation further down to do the plotting, but that's actually not critical for this particular example. So this is where the communication takes place, and we're going to print this when the processor is rank 0. Only one processor has to write that, so we choose this processor to be rank 0. We're going to just say, oh, fetching remote data, and that's going to give you an idea of how fast that communication step is going to take. Okay, finally, we have more code here that does some plotting, and we're going to use matplotlib, which also builds with UV-CDAT to do the plotting, and that's mainly because I want to show what the domain decomposition is, and for me it's a little easier to do that in matplotlib than in VCS. Finally, we have to clean up things. We have to free the windows, the MPI2 windows that we used in order to run the application. So to summarize, we're going to run an application which is called apply Laplacian to atm temp, and that application is going to read temperature data. It's going to read different kinds of data, different slices of the data on different processor. It's going to apply a Laplacian operator to the data, and then gather all the data to create a plot. Let's see how that works, right? So you would type mx mpi exec. That's the command that we invoke each time that we have to run an MPI program. In our case, we have to be slightly careful because we want to invoke the mpi exec command that comes with UV-CDAT, that was installed and built by UV-CDAT. Everything has to be consistent. If you have several versions of MPI installed on your system, then be sure to use the one that was built by UV-CDAT, or which UV-CDAT used in order to build. And of course, we're going to use a number of processors -n. I'm running right now on a laptop which has 4 cores, but just for illustration purposes, I'm going to run on 20 processors. Then we're going to invoke the Python, again being careful about the fact that we're using the Python that was built by UV-CDAT. And finally, we have our application, which is a Python script, and if that takes other options like, I don't know, plot or something like that, then you can always add them at the end. So let's go. So this is in real time. I'm not cutting anything of the movie, so it gives you a little bit of an impression how fast that thing goes. First, we noticed that there was a little lag when we started. That's because we have to sort of load all these shared libraries, and there's also a startup time for MPI processes. The next thing that we see is that we have, we see the size of our domain, the global domain, 145 times 192, and that this is going to be decomposed into 5 times 4 subdomains. The other thing that we've seen is that we actually finished the calculation at this point. I mean, we in this plotting phase of the program, and that actually takes quite a bit more time than processing the data. So I'm going to just stop here with a Control-C, just for the sake of brevity, and I'm going to just look at what the result is, because I ran the program a little bit earlier. So I'm using the display program on Linux, and that's what we're getting. So what we see here is a that domain here. We see the temperature, the Laplacian operator applied to the temperature, and we see the 20 domains, and that's about all I have to show. So thank you for your interest. Thanks.